working at Meta in the FAIR lab for almost 6 years, recently working on things not just related to linguistics and cog-sci, but also to making the large models that you see. So I actually contributed to the Llama 2 language model that Najong had on her slides. And I can say it's very different than normal kinds of collaborations with academics to work on training these big models. So one of the things that we've been talking about in Meta is how exactly our evaluations for language models and other NLP tools have changed since this kind of boom of language models being used for all sorts of things. So first, since we're in this session in particular, I want to know that there are tons of useful contributions from linguistic cognitive scientists to the creation of large language models. And I think that's going to continue to be the case. So at least I think any possible subfield of linguistics, say, can contribute useful things to LMs, has contributed useful things to LMs, and continues to do so. So definitely keep sending linguists our way. I think the three main contributions that I particularly have worked on, and I think are represented reasonably well here, are contributions to all things data. That would be things like human annotations, data set curation, doing multilingual work, also user research. Do people like talking to the thing? And this is one of the major contributions of language scientists now in the industry. This would also be the box in which I would put things like reinforcement learning from human feedback. That's where the human feedback is. Another important aspect, which I think there's a lot of excitement about, given so far what people have been saying in the panels and in talks, is on interpretability and analysis. So can the models generalize things that they haven't been trained on? If we can cut pieces out of them, what happens? Robustness, do they work well? Do they work the way we expect them to? Things like interpretability, which of course David was sharing some information about in the morning, and explainability. So can we figure out how they actually work? This is another huge component that people with language backgrounds contribute to. But I guess in our section, this portion, we've been mostly talking about eval. And this is the part that I probably spent the most time on recently. And so this means that people with backgrounds in linguistics or cognitive science have helped figure out how do we test if the models are actually working. So this could be like performance evaluation. Do they perform to spec? Maybe what even is spec? I mean, I don't know, it's a bit of a spicy one, but yeah, still up in the air. But also things like, is a model safe? If you deploy it in a product, is it going to say something offensive to somebody? Is it going to treat people the way they should be treated? Is it going to use stereotypes? What's going on with that? How do we check? And then the thing that I've been kind of most interested about recently, which is kind of meta evaluation. Are our evaluations good? Do we trust them? Do we need new ones? How does that process go? So I'm going to focus on this one. So to take a step back, I mean, Chris, when he explained one of the goals of the session, started off with saying one of the historical contributions from linguists and language scientists is, of course, as inspiration to machine learning overall. I think that's definitely true, still a possibility, but maybe a little bit more nearer to today, kind of, but recent enough. NLP was kind of firmly multidisciplinary. There was a bunch of people who identified as engineers. They were interested in solving tasks with real world importance. This would be things maybe like machine translation, possibly monetizability, other kinds of important things, or utility, as Najong put it. And then there are folks that are interested in it as science. So can these be models of cognition or something else, maybe models that approximate behavior? And these things would rely on classical linguistic concerns like what is constituency for constituency parsing and that sort of thing. And these were always kind of two halves of the field, at least as far as I know. Maybe those that were on longer might say they were one, but as far as I was there, they were two. And people might, pick and choose from each, but generally a given individual will be more firmly on one side than the other. And tasks that we decided we wanted to test for often targeted core human competencies, and both the engineering side and the science side will work on these things. And these core human competencies that at least the cog types were interested in were things that any typically developing adult human would be able to do. So you can think about natural language inference as Tom described it. It's something that you don't need any special training for. You could grab somebody off Mechanical Turk, off the street, ask them to tell you what they think the relation between sentences are, and generally they should just be able to do it. Nothing special needed. And domain expertise in language helped people pick these tasks precisely for this reason. Picked things that everyone would know, core human competencies. So how did this exactly go? People would come together to find the task that they're interested in, assemble a data set of examples of that task, a bunch of, let's say, sentence pairs in the case of NLI, and then train a model on it. Then step 3, people would evaluate the model either on similar data, perhaps from the same distribution, to see if the training worked. And then you would have an accuracy number that works 90% of the time. Occasionally, you could also take a pile of data from a different distribution, test on that, see if it transferred. This is kind of the classical way. And from this process, you could draw all sorts of conclusions. Let's say about maybe the learnability of a specific linguistic phenomenon, or you could say, oh, the machine translation system works, fantastic. One thing. So you basically have this process and then decide from there what you want to do with the model, what you think the model is supposed to mean. Now, of course, this relies a lot on having a good, strong evaluation metric. That's the thing that gives you the performance number. And so how does that play into the actual training of the model? So the main thing of evaluation, which I think the other two folks in the session brought out, is that evaluation can expose failures and suggest specific ways to improve. So ideally, we'll have a healthy cycle of evaluation. So first, you create your model. The modelers, usually engineers, will design that for the task that we talked about with the data that we selected. And then step two, the evaluators will perform evaluation on that. Maybe you run that predetermined data set, get 90% accuracy. That would be step 2A. But also you can explore the model a little bit. Give it stuff that's not maybe directly from its distribution, see where it fails. And then if there are a lot of failures, maybe you collect a new data set, specifically targeting that, figure out how it does on that, get a better kind of more trustworthy measurement. And then here's the important bit. Then you get to step 3, where everybody collaborates together. You take the failures that you discovered from evaluation, you bring those back to the modelers find out where the problem was, maybe using some interpretability stuff or something else, and then everybody will collaborate to come up with a future model. So this is the ideal situation. So this would be, then you return to 1. You have a better version 2.0, better than the first version, and you do the whole thing again. And this is how we used to, at least ideally, progress. Now, this sounds all well good. And that was kind of the old way. You have a single task, you test on that task, maybe some variations, but it was very much a task for a specific thing, for small variations among it. More recently, though, people have been working on these general purpose models under a particular paradigm called pre-training fine-tuning, where everyone's kind of presupposing this, but to make sure people are on the same page. Basically, you train a model on a big pile of data. We call that pre-training. And the task that people have been pre-training on recently is language modeling. That's the name of our whole thing, but there used to be other things people tried as well. And then you kind of fine tune it on a smaller task to do anything else you want later. So you can kind of tweak it, direct it in another direction, and then you're basically refitting it to a new distribution. So what you do is you can rewrite your tasks in unified format and basically use your kind of base model to do anything you could possibly want. And so this change from the old system to the new system has really long-ranging consequences, actually, and how those of us in cognitive science want to feed back into our interactions with language modeling, at least in the eval. So as this goes, the role of evaluation has been shifting. So if you look at over time, like the plot here, on the X you have time, starting in maybe 2000, ending up about now. On the Y you have performance. So even though the x-axis is time, you can also think of this as the size of models growing, the size of data sets growing, the number of evaluation data sets growing, the compute needs growing, and the field size growing. So tons of things are growing as we go out there on the x-axis. But basically, since the inception of this pre-tuned, fine-tuned paradigm, basically maybe 2016, 2017-ish maybe, you can see that a lot of these data sets that we were using for evaluation, the models start reaching or exceeding human performance on them. And if you start with MNIST, which was a really, not even a language data set, I guess you try to figure out if a number is an 8 or a 7, just a handwritten digits data set. It took about 15 years to go from the inception of that data set to a model being able to beat at a human level. If you go towards the right here, now we have some more kind of natural language understanding, takes about 1 year. There's newer versions of this. We're not even at a year anymore, we're at 6 months. So you create linguists or cognitive scientists come and make a really awesome data set. They work for a year, and all the models can beat it within 6 months. So it's a very crazy situation. And what that means is that with these quick improvements, modelers want more evaluations. The ones that we create very carefully, like with Mahjong, make sure you have all of these different things that you've controlled for and everything else. They're not fast enough. It takes about a year to create a high quality data set that's linguistically informed for some phenomena you care about. And it's just really hard to keep up with the speed at which these models are now beating everything. So changes in this pre-training paradigm, exploded accuracies, speed of model performance improvements is shifting a lot of evaluation away from our core competencies as linguists and cognitive scientists. And yeah, sort of an issue we need to think about. Of course, like I've been talking very rosely about our interactions between engineers and cognitive scientists, but it's never been exactly fully connected together. We've never been like marching happily hand in hand into the sunset. There's always been some disconnects. I showed you this lovely little cycle. Ideally, use evaluation to inform the new model. To be honest, modeling updates rarely, if ever, actually consider the failures uncovered through evaluation. I mean, the current recipe is more compute, more data equals state of the art, bigger, better, do more, do more, do more. So actually where we probably are is something like this. A new model comes out, a bunch of people run to evaluate it, and then whoop, all that information is gone. A new model comes out, everybody runs to evaluate it. Oh, new model comes out. It's like the circle is completely broken. So why is that? How do we fix that? Clearly, there are some hard technical issues here. For example, it's very hard to precisely locate the source of failures in models. Also, as the models become more complex with more different subcomponents, it's hard to pinpoint exact failures in all those subcomponents. It's not just the LM, it's your LHF, it's everything else. Where exactly, like cascading errors kind of throughout that are very hard to localize. So it's kind of hard to fix that. There's also some sociological problems. People who are good at evaluation are often not as good at the modeling, so they really need to have connections there, friends that they can rely on. Also, training is getting really expensive, something I'm sure NSF funder folks are talking about quite a bit. Also, leaderboard climbing is highly incentivized. If you're at the top of that board, beating all the data sets, everyone thinks your model's the best. So they use it for everything, cite you for everything, that sort of thing. They would rather employ it as their own product or something. And also just the fact that it's really slow to make high quality evaluations. And that means it discourages people from making evaluations too. If it takes a year to make a data set and it's gone in 3 months, it's a bit tricky. You spend a year of your life on something that's basically gone in a flash. So there's a lot of kind of practical considerations that make this a hard space to be working in. So this disconnect, I feel like currently it's widening. Maybe the difference is becoming all-encompassing. Pressure on modelers to release newer, bigger, better models is increasing. That's largely because these are getting productionized across the entire industry, which means that people need to demonstrate performance gains over alternatives. And that means you need evaluations to show that you have gains. Because if the earlier model beat all the past evaluations and so do you, well, you look the same. So you need a new evaluation to show that you're better than your competitor, right? And so this has resulted in modelers themselves kind of coming up with their own evaluations, which are completely disconnected from cognitive science tasks, completely disconnected. Often they're very creative. I'll show you some examples, it's pretty fun. But what that means is that our competencies are not necessarily as closely tied as they might have been a bit ago. Also, we've seen an absolute explosion in evaluations. This is an example from Google last year, I think. The Big Bench data set, it has 214 different evaluations. So that means you get 214 performance numbers. You have to aggregate somehow. It's all very complicated. And so let's say you do well on like 200 of those and badly on 14. Well, there's 200 of them. Like, do failures really matter at that point? But you're doing so well on these. So you end up in this situation where it's hard to actually balance success and failure. You don't know which one is more important. And it's impossible not to fail on something if there's 214 tests. Right? It's like just luck of the draw. You're going to miss something for sure. Another fun thing is that modelers have just decided to evaluate on completely different stuff. So a lot of us have been talking about cognitive tasks, things that are like core human competencies, like understanding hierarchical structure, dealing with negation, entailment. Nowadays, a lot more evaluation data sets are coming out for things like academic and professional understanding. This would be the stuff we teach our undergrads. So math training, chemistry knowledge, US history. This is not a general human capability to know about US history. It's a very specific, temporally bounded, particular culture, all of that. So it's kind of going more in this direction, things that I don't know, some people might want to automate. So there are still challenging evaluations. A lot of them exist. But since there are so many, it's easy for them to be ignored. So it's easy for the models to look like they do everything well, because if they don't do something well, we did well in these 200 other things though. So it's a good pile of success, maybe a medium, smallish pile of failure. There was a really interesting challenge last year called inverse scaling, when bigger isn't better. And they've tried to find tasks that bigger models actually perform worse at. Some of these have already been succeeded on since, but you can kind of think of this x-axis is roughly the same as the time x-axis maybe. This is model size. And here are at least two examples. Modus tollens, syllogistic reasoning, make bigger models, you don't succeed. Redefine, which is, use a different definition for a known term. Models still struggle on that. So there are things that are still challenging, but they are ignorable, unfortunately. Also, people are just trying crazy things, not trying to call anyone out. I hope no one's in the room that was on this paper, anonymized. But last year, a preprint came out that said that an LM could fulfill the graduation requirements of any major in mathematics and EECS at a particular famous university. What they did is they took the tests from an undergrad exam, fed them into the model, took the model's responses, and then fed them back into the model and said, were these right? So basically, research asked the model to grade their own output, and it should be no surprise the models got basically 100% correct. Because why would they have answered the question that way in the first place if they didn't understand it, or if they didn't think that was the right answer? So people are just kind of so overwhelmed with the number of evaluations, the speed of change, that they're trying things that are a bit kind of out of the realm of what we might want. Other fun things, people just come up with something that might be shocking. Can we ask the model if it can generate a unicorn using the TICS graphical software? Is that a cognitive capability you guys work on? I don't know, I hadn't heard of that one. But it does, it's pretty impressive. So you throw in this question, draw a unicorn in TICS, and this is the output from GPT-4. Unfortunately, it doesn't really replicate, but it's very impressive. Like I can't draw a unicorn in TICS, but all of a sudden the model can. So there's no way in which this is like a cognitive capability we only to have, but it suggests that something interesting is going on. It's something that you would never have expected. Shock and awe and surprise. Maybe GPT-4 is better than everyone else. So there's kind of a new way of evaluation, which is just to surprise people, to get their attention, to make them want to use your model. Which is not quite the same as having a rigorously defined linguistic program or cognitive scientific theory or any of that, but it seems to be where we're part of where we're going. So yeah, lots of things going on. This seems to be a trend. Given where we are, one might suspect that the role of evaluations is shifting a little bit, shifting away from core competencies from people like me and maybe those of us in the room, away from things like providing an understanding about model performance, figuring out failures so you can feed those in to make a better next version. And maybe it's shifting more towards something like, I don't know, supporting marketing initiatives or something else. So what does the role of a cognitive scientist look like in this kind of post-LM world? What do you guys think? This problem keeps me up a bit. Yeah. Well, there's many things where we could go from here. But one thing that I've been thinking about is like, what do the modelers actually want help from us on? So when I first started working in industry, about 80% of the asks I got from modelers were, can you make me a more challenging evaluation? I still get those sometimes. Some people still want those, still worth doing. But now maybe about 80% of the asks I get are to help determine which eval is informative. So of those 215 tasks or all these other ones that are hard and not following, which one is the one, or which ones are the ones that they should report? Which ones are the ones that they should try to train their model for? How do we decide what we want the model to do, basically? And so this is something they really want our help with. And I think that's an opportunity for us to try to redirect some of this back towards the cognitive questions that we care about. So here are some of the problems. There are many more. Other people talked about them. But the three that I talked about today is like data sets are saturating, which means all the models do basically human level on them. Obviously, we need more high quality data sets. So something we can still contribute. It's hard to evaluate general purpose models because we don't know what purposes they might be used for. Well, we could think about defining a well-motivated task taxonomy that actually figures out what it is that a general purpose model would do. Maybe we need memory, maybe we need planning, maybe we need something else. These things that all interact with language, maybe related to it, but are not maybe, at least right now, well tested for. Too many evaluations. What does it all mean? For this one, I think the only thing we can do is do more meta evaluation. And this is what I've been spending a good amount of my time on recently. I'm not going to talk to you about all of it because, papers are out there. But just briefly, I think that there's good space for a research program in meta evaluation. It's a process of evaluating your evaluation. So do they correlate? Which ones are useful and informative? Do they have kind of weird statistical artifacts in them that enable you to do well without, right for the wrong reasons sort of stuff? This would include things like ongoing validity checks for the life of the data set. So if you find some errors in it, you take it down, maybe don't use it for the next version. Things comparing across test sets for the same capability. So I did a project recently on compositional generalization. There's like 20 data sets for this. Do they all measure the same thing or not? To what extent do they measure similar or overlapping, unoverlapping? Can we disentangle that? This stuff is really interesting. Checking in with domain experts on state-of-the-art understanding for a particular capability. So we should have people who cover these things. Maybe I can do compositional generalization, but maybe other people should do other things. And then finally, kind of synthesizing what we have learned from these data sets. Tell us which ones are in order, which ones need to go, which ones need to be replaced, which ones need to be extended. And so this is, I think, one thing that I'm hopeful more people will be working on in the future. Okay.